Good morning, friends. Welcome back. In the previous section, I tried to explain about the shading problem of PV and how we can overcome that problem using bypass diode and the blocking diode. In this session, we'll continue with the same problem in couple of slides, and I'll try to explain you about very important concept. If we can connect the photovoltaic with particular load or type of the DC load, then how such load will operate, and if it will not operate as per our choice, then what are the remedies. So let's begin. So these are the major contents of this video. We'll start with the simplest solar PV system, the hotspot generation of PV system if the modules are shaded for longer time with its some thermal image that has been downloaded and tested from the Google itself, and the current versus voltage curve for various DC loads. So this is an example of simplest PV system. Over here, PV is connected with the DC load through some terminal. Now, in the same case, if it is connected with the DC load, then the load will operate with the change in radiation. But during the night time, if this load is battery, then there is a problem of reverse power flow, because at night almost radiation from the sun is zero. So at that time PV is nothing but the material. It has some RS and it has some RSH. There might be a reverse current flow that must be blocked. So this is what the simplest PV system, which is the blocking diode. No converters, no buck boost converters, nothing will be there over here. Just only PV, blocking diode and the DC load. What is necessity of the same? The system shows in the figure allows the battery to leak the current back through the PV module at night, which raises the question of whether it might be worthwhile by adding the blocking diode. So this is what the concept of blocking diode. In previous case, means in the previous video, I tried to explain for multiple modules. Usually this block signifies the buck converter if I repeat, if the PV module is used for the battery charging application. Sometimes for the battery charging application, some self-regulating modules are used. If the PV system has a charge controller, it automatically prevents the battery from the overcharging. For very small battery charging system, the charge controllers can be omitted if the modules with the fewer cells are accommodated purposefully. Such self-regulating modules, sometimes comprising of 33 or even 30 cells instead of usual 36, to purposely cause the current drop off as the battery approaches the full charge as shown in figure. So this is what the concept of the self-regulating modules. At the later afternoon, our radiation goes down, so at that time the short circuit current of the module will be reduced, and as the temperature is high at late afternoon, a significant change in the open circuit voltage of the PV module is also observed. Our next topic is the hotspot generation. Now, if the operating current of overall series string approaches to short circuit current of a bad cell, that is nothing but the shaded cell, then the overall current will be limited. Over here, the contribution of the power of this cell will be reduced, and hence it has been written as a current, means the voltage will be dropped. So later on, for the long run, this cell will become a bad cell, that is known as the hotspot. This is an example of the hotspot generation that has been observed. It might be due to the unawareness towards cleaning, that is, we are not able to clean the bird droppings from the PV module, or aging effect of the PV module. Then this is the thermal image of the dropping part, where your cell might be damaged in converting into bad cell or the hotspot. In similar cases, if you can consider the color which is towards reddish in nature, at that time some hotspot cell that has been observed in thermal imaging camera, that is what we called due to dust particle in the same, because in almost all the applications the PV modules are open towards sky, so there is a problem of dusting is much obvious. Our next segment, that is most important segment of the IV characteristic of load, particularly electrical load. So one of the basic simplest PV system is that, say for example, we are having hat or a cap. Usually it is of toy cap, where we can have a small fan towards our forehead, and we can turn on and turn off using one switch via battery. So instead of that, the small PV cells are connected nowadays. So if my radiation is high, the speed of the fan is high. If my radiation is low, then the speed of the fan is low. Means there is no regulation or any controller or a converter over there. So it is nothing but the DC motor. So likewise, how we can connect such load with the PV and how it will operate without any converter, that is what the main task. So before starting, the user or a student or whomsoever is going to run this video, they need to check the basics of IV curve of PV module and the concept of the operating point. Now I will try to explain the concept of the operating point. Usually we are having the IV curve with us. If we can connect the load, then there is also an individual IV curve of the load. And if you can plot both the IV curve on the same graph, the point at which IV curve of the load intersects the IV curve of the PV module, that point of intersection is known as the operating point of the load. So this is what the load. In this case, we don't know what is the type of the load, but the power is nothing but voltage into current, because it's a DC power, and this is what the random IV curve of the load, and this is what the IV curve of the PV. So the operating point at which the IV curve of the load intersects with the IV curve of the PV. So in this case, this is our operating point. Likewise, the current versus voltage curve for different amount of load, and we will check the operating point. So first of all, we will define it. So let's begin. The photovoltaics have an IV curve, so do loads. As shown in figure, the same voltage is across both PV and load, and the same current runs through the PV and load. Therefore, when the IV curve of the load is plotted onto the same graph as I have discussed, it has IV curve of PV, and the intersection point is one spot at which the PV curve and the load point are satisfied. This is known as the operating point. Suppose this load is resistance. So if you can model in terms of current, then I equals to 1 upon R into P. When plotted on the current versus voltage axis, it is nothing but the straight line, but with the slope of 1 upon r. The slope equals to 1 upon r, higher the slope, lesser the r, lesser the slope, higher the r. So as r increases, the operating point where PV and the resistance will intersect move along the PV curve from left to right. In fact, that is suggested that a simplest way to actually measure of IV curve of PV module. Usually in field practice, we are having the rheostat and we will vary the rheostat to plot the IV curve in the field. So the power will deliver, that is depending upon the value of resistance. You will get also one point where the maximum power will be delivered, that is also known as RM. It is the ratio of Vm upon Im. If you can familiar about the data sheet of PV module, then you will be able to recognize the point Vm and Im as maximum power point voltage or current, or it can be also known as peak power point where the rated voltage and rated current has been observed. This condition will be satisfied at STC, that is standard test condition, that is 1000 watt per meter square and 25 degrees centigrade temperature. Similarly, we will connect the PV module with the resistance or a rheostat. In this case, the R will be vary from its minimum value to maximum value. We have a multiple operating point with different slope of R, but at MPP, that is maximum power point, we will get RM, that is resistance at its maximum value, equals to Vm upon Im. So this is how the resistance will operate on the IV curve. You will find n number of lines over here. In this case, n number of lines here, 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 here. So in this case, if my R is less, or we can say bypass, I will start from ISC. If I am incorporating entire resistance, I will stop at VOC. But in that case, we will have n number of operating points of different values of resistance that has been observed. So, insolation is direct normal solar radiation is 1000 watt per meter square. So if you have fixed resistance at load, we have a multiple MPPs. So how this MPP, that is maximum power point, will be deviated? So the efficiency of the PV module with the fixed resistive load designed for the one sun condition. One sun means the 1000 watt per meter square. If you have an example of flat mirror, there will be a one sun on it. If you can reflect it, if you can cut that mirror into two portions, it could be a two sun, but its effective area will be half, or depending upon how you are cutting the mirror. So we are considering a one sun only. So the solid maximum power point dots shows the operating points where it could result in maximum PV efficiency in this case, but you will not going to track the MPPs when the radiation will go down. So such maximum power point trackers are incorporated as an interfacing unit using buck or boost converter depending upon the application to track this MPP point. I'll try to explain the same thing in my upcoming sessions. But over here we are considering the various operating points at different radiation. In the first graph, we kept, means in this graph we kept the insolation common and we are varying the load. In the same case, we are keeping the fixed load resistance and we are varying the climatic condition, that is the radiation, and hence the temperature over here, because as the radiation is more, temperature is more, and there is considerable decrease in the, or a decrement in the open circuit voltage of the PV. Our next load is the DC motor. It is the most versatile load used in the PV pumping application. So if you can have the IV curve of DC motor. So the equivalent equation of the voltage is I into RA plus kW, where kW is known as the back EMF. Usually a DC motor runs at nearly constant speed for any given applied voltage. Even then, the torque requirement of the load is changed. For example, as the torque requirement will increase, the motor slows slightly, which drawbacks the EMF and allows more armature current to flow, because the torque is proportional to armature current with the constant flux. So it delivers the more torque to the load and regains almost all its lost speed. But if we can connect this motor with the PV, at that time what is the problem that we are going to face? So this is the electrical characteristic of permanent magnet DC motor. It means that from this characteristic, this motor requires high starting current at lower starting voltage, and then it will, when it will regain its torque, then it will start. So how we can fit this IV curve of the motor in IV curve of the PV? So let's check. So this is what the case. Some startup current is required over here, and then the motor will start. So the DC motor, particular IV curve on the photovoltaic IV curve for varying insolation. In this example is somewhat exaggerated because the motor won't start spinning at 400 watt per meter square, but somehow will get high starting current due to some control techniques or converters. Then it will start. Once it will start, it will require very less radiations to keep it in running mode. It means that during early morning and late evening the motor will run, because it needs only 200 watt per meter square energy to run, means low radiation. The mismatch of operation with ideal MPP, in this case it is apparent. Notice that the exaggerated example that the motor doesn't have enough current to overcome the static friction means it has to start at 400 watt per meter square. Once it starts spinning, however, it only needs 200 watt per meter square radiation to keep it running. This could be mean the fair amount of insulation is unusable in the morning while motor struggle to break loose, which adds to inefficiency of the PV motor setup, or we can say PV pumping setup. The device known as LCB, that is linear current booster, is used to help this loss when the radiation is low. So the LCB is nothing but the linear current booster. It will convert the low current high voltage into high current low voltage. So the problem of low current at 200 watt per meter square is converting it to high current. So motor seems to be working, or it will start, it is look like the current at 400 watt per meter square at low radiation, less than 400 watt per meter square. So it will start. So ultimately the LCB is the solution. It will convert your high voltage power into high current low voltage power, so the motor can start it earlier in the morning. However, at the initial part, the motor will start at the slow rate, but some of the water will come up from the groundwater to the ground at the lower rate, though it is lower rate, but it is in the working condition. This is what the example of the DC motor connected with the PV module, and these are the operating points of the motor at different radiation. Our next curve or next load is the battery. When the PV is connected with the battery, and if it is the ideal one, then it might be a straight line. An ideal battery is one which the voltage remains constant no matter how much current will draw. But as the DC system are poorly regulated, there is considerable reduction of the voltage has been observed in the input side because load will throw some current. So a real battery on the other hand has some internal resistance. If you can model a battery voltage, it has been voltage equals to, that is terminal voltage equals to, is VB plus RI into I, which plots as slightly tilted straight line with the slope equals to 1 upon internal resistance of the battery. During charging, the applied voltage needs to be greater than the VB, and VB itself increases so that IV line slides to the right as shown in figure. While during discharging, the output voltage of the battery is less than VB, but depending upon that equation will be changed, and the slope of the IV curve line flips away and the IV curve moves back to the left. That is the discharging part. So in the charging and discharging, the input voltage V is greater than VB, and it is the charging. V is less than VB, then it is discharging. Now if you connect this thing with the PV, then either my PV has to operate at the battery voltage or we need to go for the buck converter. So if we can have a PV over here, we need to go for the buck converter, so the voltage will be stepped down at the voltage of the PV. So how we can charge a 12 volt battery using PV? Suppose a nearly depleted 12 volt lead acid battery has open circuit voltage of 11.7 volt and its internal resistance of 0.03 ohm. Then the first task is, what voltage would PV module operate if it has to deliver 6 ampere current to the battery, means charging of the battery. And second, if 20 ampere is thrown from fully charged battery with the open circuit voltage of 12.7 volt, what would be the PV module would be operating at? So at the first case, using the PV, that is PV voltage would be V equals to VB plus RI into I. We have a battery voltage that is 11.7 over here, plus internal resistance into current, because what we need to deliver a 6 ampere, so the voltage is 11.88. While drawing 20 ampere current, the equation will be minus because we are considering now load voltage. So VB minus I into RI, that is 12.7 minus 20 into 0.03, that is 12.1 volt. Since the voltage of the PV operate at its determined by the battery voltage, that would be at 12.1. So the connection of the PV is what we have done at the initial part over here. This is what the connection with the PV connected with the blocking diode. These are the converters, and this is your battery. So this is how it will operate. Now if you can talk about the IV curve, so we can draw IV curve over here and we will check how it will be respond, and it is already covered in the last lecture when we have discussed about the shading of the PV and how the operating point will vary with the example of the battery charging. Now to optimize this efficiency, that is charging efficiency, people are also accommodated the maximum power point techniques, that is what we call MPPT techniques, to be incorporated with charge controllers or buck and boost converters. It will be covered in the next class. I am very much thankful to all for your patience listening. Thank you very much.